Hi there, and welcome to Whitepaper Weekends. Today, we are going to take a close look at a paper that laid the groundwork for many of the high availability systems we rely on today. But before we get to the paper itself, let's start with a scenario that every engineer has to face and think about. So, you have a critical stateful service running, let's say it's a database, and then something unexpected happens and the hardware fails. Oh, the server is down. Now, you have a client that is sending requests and it expects your systems to be available. Now, your server is down, that means your server won't be able to respond to any of the outputs, that is, it is unavailable. So, how do you mitigate this scenario? So, normally what we do is we have a standby server ready. Now, it can be in a cold state. Cold state means it is not receiving any updates. It will have to be provisioned from the scratch without any state of its own. So an engineer will have to come up, provision it, and then ensure that the state is as it was for server A, and then ensure that the load balancer points to server B, and then it can serve the request. Typically, this takes hours at time. Or you could warm it up a bit. It's not containing the latest data, but it does contain some amount of data. So now your only task would be to come up. You don't even have to come up, you just have to trigger a sequential copy and make the server B synchronous with what server A's state was, and that is how you do it with warm startups. But you would often lose out on any active connections that was there with server A, and any transactions that were in flight. So in both of these situations, the common thread is a period of service interruption and potential data loss, as you can see. So this is a problem that a team at VMware tackled. They asked, what if we could build a system where the failover is instantaneous? I'm not sure if you can see the title of the paper, but it says, it's basically a fault-tolerant VM's design. So how can we ensure that the failover happens nigh instantaneously, and no one, not even the client, not even the internal system, is aware that a failover has happened in the first place? How can we make that a reality? How can we implement it? How can we make it practical so that it can be used in real enterprise systems? So I'll be attaching the link to the paper down in the description below, so you can go ahead and read through that if you want to. But now let's get started into the paper. So there are a couple of ways. There are some ways to maintain high availability, and one of the most common ways is a primary and replica approach, in which we have a primary server that is responsible for handling the live traffic, and it responds everything. And then we have a backup server in place, which will be there just in case of server A fails, so that we can fail over to server B, and now instead server B will be able to send back the responses and handle the live traffic. So in order to do that, we have to ensure that the state between server A and server B is in sync. Now, how do you ensure the sync? One of the simplest solutions that you could think of is that all of the state of server A, its CPU, its memory contents, its IO, everything, every change in its state will have to be sent over to server B. Now you can imagine that the bandwidth required to transfer this amount of information would be quite large. How can we do this without incurring such a huge cost? So one of the alternate ways is to think of these stateful servers as a state machine. A state machine comprises of multiple states that your server could be in, and your system will move from one state to another state based on the input it received. For example, if you are on state A and you receive, let's say, some input smaller, you will go to server B, you will go to state B. Now from B, you received another input, let's say C, so you ended up at C. On the other hand, let's say A, you received, instead of input A, you received input X, so you end up at position X, and then you can have a loop back into the same. If you have a Y, you are in the state Y, and then from Z you can go to Z. So this is what a state machine looks like. You have different states, and based on the inputs, the final state could be different. So the theory is that if we have two state machines with the same initial start point, and if we give both of them the same sequence of inputs, they will inevitably end up on the same final output. So we need not transfer the entire state at each instant of time, entire change in each instant of time. We only need to ensure that both the servers that both the systems are in sync in the initial phase, are started from the same initial point, and then we feed them with the same sequence of instructions or operations so that we can ensure that server B is in sync with server A. So in case of server A fails, server B can almost instantly start serving the traffic with minimal downtime. This is what the basic premise of the paper is. How do we make it into fruition is something that we will have to discuss about. So mind you that we are discussing this fault tolerance on VM technology, that is virtual machine. Why was virtual machine used for this? Because in a normal processor, let's say you have a 4 GHz processor, it processes 10 to the power 9 operations per second, which is quite fast. And now if you have to ensure that these two systems are in lockstep as in they are executing one after the other, not one after the other, but like they're executing in near sync. The backup would be a bit behind, of course, than the primary, but they are still executing in sync. So if you have 10 to the power 9 operations done in 1 second, that's a lot of compute, and you will have to almost continuously send the traffic, which won't be feasible in the long run. And of course there are other operations as well. So you have inputs, you may also have some non-deterministic events. We will elaborate on that further. So how can you ensure that this particular information is carried over to the server B? You need some mechanism that can capture all of these events that are happening in the primary server A in this instance, and then relay it to server B. For that we use virtual machines. Now a virtual machine runs on a physical hardware, that much is obvious. So now a physical hardware, you have your physical hardware, excuse my terrible writing. So you have your physical hardware, on top of it we establish a hypervisor. A hypervisor is kind of a coordinator which will handle multiple VMs that are running in the same physical hardware, and each of this VM will feel like it is the sole occupant of this entire physical hardware. It is the sole being that is using the entirety of the physical hardware, but it is an illusion that is provided by the hypervisor. So you have your virtual machine executing here. So this is your primary server, and inside your VM you will have a guest OS and you will have an application. Let's say our application is the DB server that we are running. So now this VM will be under the influence, under the assumption, or not the assumption, under the illusion that it is the sole occupant of the entire system and it will be interacting with the physical hardware. But we are not having it directly interact with hardware, but instead we are having it interact with the hypervisor. So all of the operations can be trapped back to hypervisor, and hypervisor will then do the necessary physical hardware activities that it has to do and then send back the response. Now all of the operations can be done by the hypervisor. We can also give it some memory to read. We can say, hey, this operation was completed. We can handle the traps. We can even handle network packets retrieval and sending out of it. So we can log all of these entries. So what we propose to do, what the paper proposes to do, is that for all of these operations in the VM, for all the inputs that are occurring, what we could do is for each of the input, we send it to the hypervisor. The guest OS traps it to the hypervisor. Hypervisor takes the responsibility of sending these events, inputs, any requests, any network IO that is occurring to your backup VM that is running on another server altogether. It could be in a different building altogether, for all that matters. So now it will be sent to the hypervisor of the backup, and then this will ensure execution, deterministic replay of all the events that occurred simultaneously, in sequence. So by doing this, we ensure that state machines are replicated. We provide them the same inputs, and they end up in going the same final output state. That is what the basic premise is. So now you understand why hypervisors are good, because it allows us to have an abstraction layer that will decouple the virtual machine from the physical hardware, and then we can log these entries particularly and have a virtual log step with a backup VM. Okay, so this is called deterministic replay. We are deterministically replaying all the operations that are occurring on the primary VM. We are not replaying the exact memory, we are not copying the memory changes. We are copying the inputs and having them execute on the backup. Now, the primary VM will be the only one responding to the clients. It will be only one handling the live traffic. The backup VM won't be doing, it will be acting in the replay mode. It will only take responsibility of replaying whatever changes it has received. So now let's get into the nitty-gritty details of how the architecture is laid out for this. So, of course, you have two virtual machines. I am skipping the drawing exactly, but let's say you have the hypervisors as well. These are hypervisor 1 and hypervisor 2, and these are running on separate servers altogether. This is the primary VM, and this is the secondary VM that we have. Okay, so now the primary VM is handling the traffic, and as soon as it receives any input, it grabs to the hypervisor. Hypervisor maintains a buffer of all the inputs that it has to process, and then as soon as it receives an entry, it tries to send it to a log channel. A log channel is a dedicated network infrastructure that is set up between these two servers so that we can send the logs. We can call it a login channel. So we can send the logs of all the events that are happening through this login channel to the secondary virtual manager, the secondary server. Now, in the second hypervisor, we will also have a buffer which will contain the results of which will contain the logs that were sent over to the login channel. As soon as we receive from the transmission, as soon as we receive the transmission from the channel onto the buffer, we send an acknowledgement back. Hey, I have acknowledged this. I have already have it written in the log file, and I will ensure that the state is kept consistent. This is also called, as in modern lingo, we call it write ahead log. We are not carrying out any operation upfront. We are instead writing it in a log file and then sending it over. Once we receive an acknowledgement, we then continue on with the operation, because now we are sure that the backup has kept track of all the operations that occur. Thus, we ensure that even in case the primary VM fails, we can switch over to the secondary VM immediately, because the state of the secondary is very near to the primary. So it only needs to execute all of the remaining logs that it has received, and then it will be able to serve the live traffic. Thus, in this way, we can ensure that downtime is kept minimal. I hope that clears up the things for you. So this is, as we discussed previously, this is the deterministic replay. Now, what can we send from one place to another? We can have some networking packets that we received. We have to log them over. Now, there could be certain requests that we have received, certain API requests or some stuff. Then we can also have discretes. And also, there could be some non-deterministic event. Let's say that non-deterministic event or operation. What do I mean by non-deterministic? Because the results of such operation or event is not deterministic, of course. In that way, suppose, let's say, for primary virtual machine tries to get the current time. That is a non-deterministic operation, because if you log that operation back to backup server, so primary VM, it asks what is the current time. It will receive a time that is synchronous with the primary server, but like if you were to execute that same operation on the secondary VM, now the time would difference, there would be a time difference. So now it's non-determinism, but you need to ensure that both of the states, both of the machines are in exact sync. We cannot allow the state to deviate, because the final output of the machines would be quite separated. I hope that makes sense. So we have non-deterministic event or operations. Non-deterministic event, think of it as interrupts, virtual interrupts, any IM interrupt. So we need to ensure that all of these are executed in sequential fashion so that we can have them replayed deterministically. Okay, so now let's come to the implementation details of all of this stuff. So we have an FT protocol, FT as a fault tolerance protocol, because we need to ensure that in order to handle non-determinism and in order to ensure that we give consistent records throughout, we need to have a protocol in place. This is not like TCP UDP, but these are just some rules that we have to enforce in order to ensure consistency. So there is one input rule, as we discussed previously as well, that is val. You have to first write ahead the log. Before carrying out any operation, as soon as you receive an input, the VM will trap to the hypervisor. Hypervisor will create a log, send it over to the logging channel to the backup VM, and then it will send back an acknowledgement for the same, and then it will start with the execution. That is the typical flow. It cannot proceed on with the execution unless we get an acknowledgement that, yeah, this particular entity has been written back. Now this, as you could think of, this might end up being a bottleneck, because hey, what if the backup is slow in its processing? Then what do we do? At that time, there are some solutions in place. That is why this is such a fascinating paper to discuss. We'll get back to that later. But the input rule is basically you have to write ahead the log first. You have to do while first before carrying out the operation. Now, there's an output requirement. The output requirement is that even in case the primary fails and we switch over to the secondary server, to the backup server or to the replica server, whatever you want to call it, we must ensure that from that point forward, any output that it sends out must be consistent with what we have already sent out to the external world. The results should be consistent. There should be no memory corruption, there should be no state divergence. So we need to ensure that this output requirement is met. And in order to do so, we have to enforce another output rule of ours, and that is that if you are to carry out any operation that can produce an output, you are not permitted to send that output further unless you get an explicit acknowledgement back from the primary server. What do we mean? Let's imagine we have two lines here. The upper one is an execution of the primary VM, and in the bottom one we have the backup VM. You get an operation. You get an output operation that you have to get back a response from. You have to give back a response. So once you log it, you have to send the log to the backup VM. The backup VM will send an acknowledgement. You will continue processing, and then only you can send out the response, provided that all of the acknowledgements prior to completing this operation have been received. If you do not do so, if you do not get a confirmation and you directly send it out, then what will be the case is that the backup cannot get it. The backup is not either. So if you do not send an acknowledgement, what happens? Okay. If you send the output as soon as you send out the response, let's say you send back the response and you send the output here itself. Now, what if the backup VM does not log it? What if the backup VM fails at that particular point? So now you will have to create a new instance, and that new instance won't be aware that this output was already set out. So there is a state divergence between the primary and the backup and the newly created backup. So it will have no log whatsoever that, oh, this output operation has already occurred. We have already sent out this output operation without logging it. So in order to maintain consistency, we have to enforce that only once we have explicitly gotten the acknowledgement, once we have gotten the acknowledgement back from the backup VM, only then can we send the output response. This is imperative to ensure that consistency is maintained in case of a failover. And again, let's also discuss one more aspect. So you have an output operation. You send the log by the logging channel, and then it is received in the backup VM. Okay, the log has been entered and it sends back an acknowledgement. Remember that it is in the backup VM. We have not started executing it on the backup VM. We have just received the log entry and we have sent an acknowledgement that, okay, I have received it. You can safely continue your operation. But what if at that point, just before sending the output, the primary VM fails? How will the backup VM know when it is switched over that this output operation was actually sent or not? Now that's a tricky situation, isn't it? So we cannot guarantee, the paper explicitly states that we cannot guarantee exactly one's delivery. The backup VM has no way of knowing whether or not the output operation was sent away, because see, we are not using any two-phase commits for two-phase commit transactions to identify whether this output was sent or not, because that would be too much of an overhead. We don't really have any way for the backup VM to know that this output was sent or not. So once it is copied over, it will again send back the response just in case. Now it specifically delegates to the networking infrastructure that it is able to handle duplicate packets, or it is able to handle missing packets or not. But yeah, this is one of the core fundamentals. This is one of the core caveats that we have to consider, that VMware FT does not guarantee exactly one's delivery of a packet. It can log it, but it does not know whether the output operation was successful or not. So just to be safe, we send out the response either way. Now let's discuss another fundamental aspect. How do you detect and how do you handle failures? because you need this to be an automated process. You don't want to page an engineer in the midnight and disturb his sleep and have it be done. So we want to avoid any downtime. So we want to have some mechanisms that will allow us to detect any failures that can happen, that has already happened. So we have these two servers, and we have a logging channel between them as well. Okay, so there are two mechanisms that we use to identify whether a failure has happened or not. First of all, both of these, let me select this. So let me select different colors so as not to end up confusing you. So yeah, both of these send heartbeats to each other, the backup VM and the primary. So this is your primary, this is your backup. The primary and the backup, both of them send each other a UDP heartbeat continuously, every second, every 2 seconds, whatever the configuration that you have set for, but it continuously sends heartbeats. If at any point we miss the heartbeat, we can assume that the primary has failed. Of course, there is a split brain situation as well. We can talk about it later. Split brain is basically the primary is working, but the network infrastructure between the primary and the backup is down. So in that case, what will happen? But we are getting ahead of ourselves. Let's focus on what is currently in front of us. So we have the heartbeats that are being sent between the primary and the backup. Also, we continuously monitor any traffic on the logging channel. If any point we see that the heartbeats have stopped or there is no traffic on the logging channel, then we can safely assume that one of the two, depends on which side we have stopped receiving the communication from, has failed, and then thus we detect the failures. Now, in case of a failure, now let's say what mechanisms we have in place to handle this. Okay, so our primary concern is what if the primary has failed? How do we handle this? How do we fail over to the backup? So in that case, what we do is, so as soon as the primary server is down, we can identify that, hey, the primary server is down. Backup, you have some entries left in your logging channel. You are lagging behind in the execution by some logging channels, so it has to execute them. And once it is executed, now we mark the backup server as live, or it is now the primary, and it will start serving traffic to the outer world. Now, mind you, it does not have a backup. So afterwards, we will also have to ensure that another backup is spawned in one of the other servers that will act as the backup for primary. Now, it will be running in live mode itself. It will only be sending out the instructions because it does not have a backup. It does not have any logs to send out. You have to remember that in order to send out the logs, there is a lot of process involved, as we discussed. The VM will have to trap to hypervisor will have to create a log entry, it will have to send it to the log channel and get an acknowledgement back, and then continue an execution. As you can see, there are a lot of steps involved, and this might affect the execution of the primary VM. So if we don't have a backup, we do not need to perform these steps. So the primary VM can continue execution in the live mode. It does not have to relay any of the output, any of the operations that it is performing. There is another engine. There is a clustering service that is set up. Now this clustering service will ensure, now all of these VMs run on a cluster of servers, and there's a pool of servers available. So a clustering service will detect whichever failure has occurred, and then it is responsible for switching over to the backup or replacing the backup wherever the failure has occurred. And then once we have the backup handed over, then we have to spin up a new server, a new backup server. We have to allocate, we have to see which other currently available servers is present, and then make it as the backup and have it serve, and establish the log connection, and then switch the primary to, hey, now you can start sending out the logs, and the backup server will start replaying the logs that it received. So this is what happens typically in a failover scenario. Okay, so this is also done. How does the clustering service identify which of the servers it has to run on? It has metrics of whatever the live CPU utilization, memory bandwidth is available for any of the servers, and decides upon the best substitution. And then it creates the bandwidth and it creates the infrastructure required, and then say, hey, now we are done, we have established redundancy now, and we can continue on with our operation that we have. So this is how it is usually carried out. Now we are done with the basics. Let me just recap what we have seen so far. So in case of ensuring that you have a backup server handy and it is able to start producing the output, it is able to start handling the live traffic as soon as possible, is to keep its state very near to the primary VM's execution. And that happens because we have modeled this entire problem into a state machine based architecture. So we are thinking of any primary VM or any server as a state machine, and if we provide them the same sequence of inputs, we are guaranteed to end up on the same output. So in order to do that, we have established two rules. One, there is the input rule, in which we have to log ahead the entries and then carry out the execution. And then the second is output rule, wherein we have to wait for an acknowledgement from the backup VM that, hey, yeah, I have logged in the operation that we're going to carry out, so please go ahead and do that. And then only after we have received confirmation from this can we send out an output, because we have to maintain consistency. There is the output requirement that in case of a failover, the backup VM must send out responses that are consistent with what has already been sent out from the primary. Its state should not be divergent. So this is the recap of what we have studied so far. This is the fundamental principle. Now there are a lot of practical implementations, practical considerations, practical challenges that were faced in this paper, and now we'll be discussing about them in greater depth now. Okay, so let me just draw a line over here, and then let's start with the first problem, physical implementation, actual practical implementation problem, and that is, how do you start or restart a virtual machine? Quite an important scenario to consider. So let's consider you have the primary VM running, you have the secondary VM running, you have a backup VM running. Now it might be the case that the backup, this is the primary server, this is the backup server. I'm calling it server, think of it as a virtual machine from now on. Now what happens if the backup server were to fail? The clustering manager will detect that, hey, the backup server has failed, and the primary server will now go into live mode. It will stop relaying the logs of the packets or logs of the operations that it carries out, and just minds its own business of carrying out the handling of the live traffic. Now the clustering manager will again see which cluster it has to create a new VM on, and it executes a procedure which is done by vMotion. It is the vMotion. So what we are trying to do is, the clustering manager, out of the many servers that we can have as many servers. Out of this we have to select one of the servers, and we have to ensure that this primary server is replicated, is copied over to the new server. So we have a new backup VM in handy. You have to be mindful that we have to ensure that backup VM is kept as close as possible to the primary VM. By close, I don't mean physical distance, but rather the state of the backup VM should be kept as close as possible to the primary server. The way to do this is via vMotion. And vMotion, how it works is, of course, we carry out the copy of the entire state, memory, CPU registers, onto the backup VM. And now, it is not the case that the primary server has stopped its execution while this copy is going on. It is writing to the disk, it is carrying out IO operations, it is updating its registers. So the hypervisor keeps track of all the dirty pages in the disk, and then in time it tries to copy them over. It copies them over again and again and keeps the backup VM, tries to get the backup VM as close to the state as possible. Then once a time comes that the amount of dirty pages is quite less, in that case we halt the execution of primary server for some time, copies the remaining of the dirty pages that had been modified by the primary VM, and then copy it over to the backup VM, and then start the execution of the primary server back again. Now primary server will start creating the log. Of course, we have to create a dedicated log channel between the both of them as well. This is imperative for our use case. So once this is created, we can start the execution of the primary server, and then it will continue its execution, and we have the redundancy established. Now, how genius is that? It is a simple enough solution. So they are using vMotion. They also modified vMotion because vMotion was usually used to migrate a virtual machine from one physical server to another physical server. Think of it, you usually do it because you have some maintenance of the server that is pending. You have some problems that could occur. So you have to migrate your VM to another server. This was done by a vMotion, but they modified this vMotion to replicate not migrate, to replicate the VM onto a different server, and that is carried out in this particular way. This particular mechanism is not mentioned. I dived deep and found other resources as well, so this is something that you will be able to find only in this video itself. Okay, so we have already discussed, so this is how we start or restart a VM. In case of a primary server failure, we have already discussed that beforehand. If you want to migrate a primary server, from one server to the other, now what you have to do is you have to first of all hold the execution of backup VM. You have to create a new server, copy over the contents, perform a vMotion, and once it is running, then you have to establish a dedicated login channel between them. Say now you can continue your execution, and the backup VM can now start its replay mode of execution, in which it will replay all of the logs that it has received. And voila, we have the mechanism of how we can start and restart a particular VM. Now, let me create a new page since we are running out of pages. Now, there's another practical consideration that we have to make, and that is login channel. So you have login channel. What are the problems that we can face in this login channel? Again, remember that we have a very large buffer on the hypervisor for the primary, in which all the operations are logged here. The hypervisor tries to ensure that as soon as it receives any log, it has to send it over to the login channel, so that it can be sent over to the backup server's hypervisor. And backup server hypervisor also has a log buffer of its own, and this is put over here. As soon as it is put over here, we send back an acknowledgement, and then it continues the operation. Now, again, there are two things. We have a producer producing the events, and then we have a consumer consuming the messages. Now, you can think of a situation in which there could be a mismatch between the rate of production and the rate of consumption. If the backup VM is executing rapidly, it will empty out its log buffer. If it empties out its log buffer, the VM could be halted easily because it is not serving any live traffic, so we can easily halt it. But in case of a primary server, what if the backup server is lagging behind? Again, this could be due to a lot of reasons. For example, the VM, the server on which the backup VM is running on, could also be running other intensive operations. What if we have more number of VMs on it? What we have more number of processes? What we have a limited amount of memory to execute? In that case, the backup VM's execution would be slower, and thus it will tend to fill up the log buffer. And if the log buffer tends to fill up, then the primary hypervisor's log buffer will also tend to fill up. Now, if it has to carry out an operation, it has to write first, but there is no space in the log buffer. In that case, it has to halt its execution. Now, if you halt the execution, the primary server is actually trying to serve live traffic. If you halt its execution, you are affecting the downtime. You are creating a downtime of your own. So we have to avoid this particular situation at all costs. So the design of this particular solution is such that the probability of filling up a log buffer is kept to a minimum. And the solution they use for this is simple yet elegant. We use a simple throttle. Remember that this is a hypervisor that we are talking about. A VM is running on a hypervisor, and the hypervisor can control the extent of hardware, extent to which the VM can access the hardware. So once we see that, hey, how can we get this information across as well? Okay, so when we send back the acknowledgement, we also piggyback upon the acknowledgement some data that pertains to what the current state of the log buffer in the replica is, how much it is lagging behind in the execution. This real-time information is sent back in the acknowledgement, and the hypervisor keeps track of this information and adjusts the execution of the VM accordingly. So if it sees that the delay is getting significantly larger, we have to slow down the VM execution. How do we do that? We give it less CPU time. We instruct the hardware, hey, give this VM less number of CPU cycles, and thus automatically we can rate limit, we can throttle the primary VM's execution. And then once we see from the acknowledgements, from the piggyback responses off of the acknowledgements, that now okay, the log buffer has started to empty up, we can gradually increase the CPU cycles and get back to it. Of course, this scenario have to happen is extremely unlikely, and this is only probable to happen when the system is under extreme stress. But yeah, you can see, have a look at the solution. It's simple, it's elegant, and it's absolutely beautiful. Another reason that we want to avoid having an execution lag is because think of it this way: if the primary server were to fail and if there's a lot of execution lag, the time it will take for the backup to go live would be the execution delay plus the time taken to identify that a failover has occurred. So a failure has occurred, you need to find that particular time, and then you have to add on the time that it takes for the backup server to sync up. Now, if you have a lot of log entries to execute, you are lagging extremely behind, the downtime will be severe. So we do not want this to happen. So we always try to use throttling based mechanisms. The paper has proposed using throttling based mechanism to ensure that we are continuously in sync and we rate limit the particular scenarios. So this was how they maintain the logging channel operations. Third operation that we have is, again, we are sending out a lot of operations via the logging channel on the VMs. So there can be multiple types of operations that has to be handled by the fault-tolerant virtual machines. Now, okay, let's say that your primary server, in case of your primary server, you have your primary server. Now, as a good engineer, you have ensured that it is auto-scalable. As soon as you see a burst in traffic, the resources that the primary server has, it has to be automatically increased. Now, how do you ensure that the backup server is also kept up in sync? Because whatever the requirements, whatever the capabilities the primary server have, we need to ensure that the backup server has the same context, because to keep the sync and to avoid overflowing of the buffers that we have. So how do we ensure this? We send out special operations via the logging channel as well. So any resource management operation that is being carried out, let's say we allocate more CPUs to the VM or we allocate more memory, there is a special type of message that we send out that ensures that the hypervisor does the same for the backup for the virtual machine that is running on the backup server. Cool, right. And then we also have to consider another operation in which I think we have already discussed about this, but vMotion of a primary VM. If you have to migrate a VM onto another, you have to send an acknowledgement. You have to send another operation, another message from primary server to backup server ki, hey, complete all of your executions that are left pending. Wait, I'm getting migrated. Once it is migrated, then the communication is established back. So that is another type of operation that is needed. Now, in case of primary server, that is easy to do, but in case of a backup server, one of the core requirements of a vMotion to be done is that we have to ensure that all of the pending IOs are completed. If a primary server has to migrate to another hardware, another server, there would be some pending IOs. IOs are slow. Any IO performed is non-blocking. So we can carry out parallel executions, and we have to ensure that all of the IOs, all of the pending outstanding IOs are completed in the primary server before we switch over to the new server. So this is one of the core requirements in vMotion, that all of the IO operations should be quizzed or should be completed before we trigger the final transformation, before we go on to the final switchover. But in case of backup servers, it is easy to do in PS. You can just say, hey, hold. But in case of backup server, it has no will of its own. It's a puppet. It's only replaying the executions of whatever is happening. Whatever events are transpiring in the primary server, it has to replay. You cannot tell the backup server, hey, complete all your IOs, because it has no log messages. It has log messages that it has to execute. So how do we ensure that this particular IO is completed? How do we handle this parameter? So what they do is, in case of a vMotion for a backup server, what we do is we try to complete all of the pending IOs that we have, and then once we're in the final switchover, we send back a message across the login channel and ask the primary server, hey, can you temporarily hold all your IOs? And once it does, we execute all of the pending IO operations, and once that is done, we migrate over to a new server. We migrate over to a new backup server and then continue the execution once the login channel is done. Okay, a lot of beautiful solutions to all of these problems are present in this paper. So we have already discussed three aspects. One is how do you handle starting or restarting of a VM? How do you handle logging channels and rate limiting them? How do you have different types of operations on FT on fault-tolerant virtual machines. How do you handle resource changes? How do you handle migrations of the VMs, etc. Then now let's get to the complicated aspects of non-determinism. Now this is where the crux of the complexity of the paper lies. So we have the paper highlights what implementation issues they have faced pertaining to disk IOs. Now, you have to remember that disk IOs are non-blocking in nature. It takes orders of magnitude more time to do a disk IO operation than for a CPU operation to do. So CPU executes, CPU says, hey, I want to read this particular page, read it for me, and then it goes and continues its work, and the DMA, direct memory access, handles the loading of pages from the disk into the main memory. Now, since the disk operations are non-blocking and they can execute in parallel, what happens is we can have race conditions here. Since it is non-deterministic, so let's say how can that happen? You have a CPU. It says to the DMA, it says to the hypervisor, basically, since we are talking in virtual context, but let's just simplify things for a bit now. It says, hey, read me the contents of page 1, 2, 3 and write value 10 to it. DMA says, okay, I will take that into my queue of tasks to carry out. Then the CPU goes back into its processing and again it sends out an instruction, hey, in page 1, 2, 3 again, write value 20. The DMA again then puts it in the request, batches it, and then once it's time to perform, it is dependent, it is created so that we ensure that memory access is optimized, the disk access is optimized. It depends on the position of the head. What is it I have drawn? But it depends on the position of the head at which it is there. So you have various disk scheduling algorithms as well. Based on that, it might be the case that we have a non-determinism. What happens is we first write 10, then we write value 20. So the end result would be 20. But if you write 20 first and then write 10, then the end result would be 10. Non-determinism. This can happen on the primary server, but if we were to carry out that same operation across the backend, then the output could be reversed and the state could diverge. How do we ensure that these race conditions don't occur? Simple solution is the simple solution is the architecture, the mechanism that we have. It detects any such potential race conditions and it forces sequential execution of them. Once it forces sequential execution of them, the log entries are carried out and replayed accordingly. This is one of the aspects. The second aspect is there could also be a race condition when a VM application and guest OS tries to access a memory page in which our DMA is trying to read a disk block into. Now, since the CPU is not blocked, it can read the memory page, but what might happen is the DMA is also trying to read the value in the hard disk and then store it in that particular page, let's say page X. Now, we can have non-determinism here as well. What if the CPU gets to the value first and reads value 10, but then the DMA reads another value and overwrites it for 20. Now, the CPU is working with 10, but the result was 20. And in case of the backup VM, what we might have is the DMA was able to write it first, 20, and the CPU reads the value 20. So now you again have a state divergence. How do we handle this? So in order to do this, the initial solution was suggested is that whenever a virtual machine is trying to access a memory page into which a pending disk IO is also going to happen, then in that case we can set up page protection, that we can lock the particular page. So if a disk IO is pending on that page, we can protect the page, and if a VM tries to access that particular same page, then a trap is issued to the hypervisor. The hypervisor blocks the VM until the disk IO completes, and then once it is complete, the VM is now able to read the page after the protection is removed. Of course, you can see that disk IOs could take a lot of time, so this is a particularly expensive operation. This is quite an expensive operation, and if you have to do this again and again, there would be a performance penalty. So what is another alternate solution that they came up was the concept of bounce buffers. You have to remember that hypervisor provides an abstraction over the physical hardware. Hypervisor can control whatever the VM has to see. So what the hypervisor does is that it says to the DMA, hey, the page that you are writing to, whatever the size of the page is, let's say it's 64 bytes, I have another 64-byte buffer in my hypervisor memory. Could you please read the page in here instead of where you were originally supposed to read it? Now, the VM can actually access the page X. The disk IO, the DMA, the direct memory access controller, reads from the disk, and it was supposed to put the value in page X, but hypervisor intercepts that call, creates a buffer of the same amount of memory, and says to the DMA, hey, instead of putting it over on page X, please put it over on page Y that I have created for myself. The DMA does the needful. The VM is free to read the pages, but once the disk IO is complete, the contents of the page Y are mem copied into pages, and then we can ensure that no race conditions are observed. Again, simple yet elegant. Okay, so this was the concept of the bounce buffers, and through this we do not have to trap to the VM, and we can ensure that we are able to get the necessary response without any blockers. Now, what could happen again? Now, because of these non-deterministic events, now since this is logged, again remember that we send out an acknowledgement from the backup server only upon the receipt of it, and then what we do is, again let me see where is it. So we cannot guarantee exactly one's delivery. So even in case of a disk IO that is being carried out, we do not know if the output was done. We do not know if the disk write was actually performed, if the IO actually completed or not before the failure occurred on the primary VM. The only way for us to do is to again replay that same execution, because memory write, reading memory or writing to memory, is an idempotent operation. What is an idempotent operation? It doesn't matter how many times idempotent, I cannot spell for the life of me today, but idempotent means no matter how many times you carry out an operation, the result is going to be the same. If you say, hey, set memory value X to, or you can say, hey, set my account balance to 100. No matter how many times you say it, even if you say it 100 times, your account balance would reflect to be 100. But if you say, hey, add add 5 rupees to my account, if you say it 500 times, you will end up with 2500 rupees in account. So the result is different. In idempotent, we are ensuring idempotent operations. In idempotent operations, no matter how many number of queries that you do, no matter how many operations you perform, the end result is going to be the same. So that is an idempotent operation. So any disk IO, even if it is failing, we can ensure to execute the same operation because it is idempotent in nature. Even if you don't know whether the primary VM was able to execute that particular operation before failover, we can still go on ahead and replay that because it is idempotent in nature. Okay, so those are pretty much the implementation details that we had to see through. There is one more that is left pending. So we discussed about disk IOs. There is another concept for network IOs. Now, in order to ensure performance in virtual machines for networking, by default implementation, the hypervisor can directly override the value, override the memory, and provide the output, provide the packet that it wanted. So what happens is VM sends out a packet, it expects a response, but it is allowed to carry on further. Without trapping to the OS, we directly send the response to a memory location and then interrupt the VM that, hey, you got a new call, you got a new response from the network. So this is an optimization that allows us to do it asynchronously. The output, the packet that we received, is asynchronously fed into the VM. Now, whenever we introduce asynchronicity, we also introduce non-determinism, because we need to ensure that this particular call, this particular operation should be executed at the same instant in the backup to maintain consistency, to maintain our output requirement. If it is a non-deterministic event, we have to take some measures in place so we can make it deterministic and have it executed in the backup. So one of the things that the authors did is they disabled this particular feature. They no longer allow the hypervisor to asynchronously update the network related memory operations. So if you don't do this, the VM will have to trap with the hypervisor for sending out any packet or for receiving any packet, and then it will add on to the performance delay. So as a result, you get a performance hit. You have to make a trade-off. You receive the performance hit. And now, but the core idea of fault tolerance is to ensure that the sync is maintained without us compromising on the primary virtual machine's throughput. We do not want the primary VM to get slower. How can we ensure that if we already have taken a performance hit? So we implement two solutions to fix this. One of them is a batching solution in which we batch the pending network request into one. So what we do is I have the notes written over here. Once again, this is the paper that we had. Okay, and let's go down. Yeah, so this is the network transmit batching sequence that currently is executed. So whenever you have to send a packet, you call the socket call, it goes to the hypervisor traps the guest OS execution, and then within the single batch process, it places the request into a transmit queue, and it pulls any pending network calls from the guest OS network buffers, and then it logs it into the backup hypervisor, acknowledges the receipt, and then it sends out. In that way, we can ensure that we do not trap on each of the network call that we have to do. So this is quite a great solution. And then what we have, another solution is the use of callbacks, or what is synonymous with a tasklet in Linux. So what a typical flow looks like is, see, you have a network call to make, you have to log the particular operation, right? So if we are able to reduce, so again, what the bottleneck is, we have to understand that you have a performance concern. You are not trapping, you are trapping the calls, and then you have to ensure that you follow the input rule. So you send a log, and then you wait for an acknowledgement, and then only you are allowed to send back. This process can take time. How can we ensure that this is almost instantaneous, that we get a receipt as soon as possible, we get an acknowledgement as soon as possible? Now, in order to send a network call, what you have is you have a thread. This is a thread. You have a thread which is responsible for sending the particular log onto the channel. Once it does, it waits for an acknowledgement. While it is waiting, the CPU, the virtual CPU, in this case since we are dealing with hypervisors, the virtual CPU blocks this thread. It puts it to sleep and carries on with another execution. So now there's a thread, there is a context switch. If I get right. So there's a context switch. The CPU removes all of the data and it picks up another thread to execute. Now, once you get back an acknowledgement, the CPU will have to perform context switch again on the current thread that is executing and wake up this thread. And this wake up thread will now then continue with the execution. So this particular context switch adds an overhead. How do we ensure that this is removed? If you have to remove this, what they use is to rely on something called as callbacks. You register a function at the very beginner stage when you are starting up the server, when you are starting up the primary VM. You register a function that will be responsible for handling this particular event type, this particular interrupt. So instead of it going to sleep, instead of putting it to sleep, what we do is as soon as we get an acknowledgement back, the CPU immediately leaves whatever it was doing and it executes this function. It executes this function and it invokes another function that is responsible for carrying out the pending operation that we had to do. So this is fast. This is quite fast, and with these two solutions, we were able to reduce the performance penalty that we got when we disabled those optimizations to ensure non-determinism does not occur. So this is how we did it. So, but of course, creating a tasklet is deprecated in Linux, by the way. And if you rely on these callbacks, you have to ensure that you follow strict programming principles. You cannot for the life of you do any complicated process, neither you can do something that will put this current thread into sleep as well. Because if it's put into this sleep, your system will end up into a deadlock situation. So this is a risky thing to do. but still they went ahead and had to do this in order to, they sacrificed on reliability so that they can get the better performance. So these are the implementation considerations that they had to follow. Again, do read through the paper, it's a fascinating paper. Okay, you will be asking, okay, we have talked all about this theory, is this really practical? So if you read through the paper, you will find out that when they use the VMFD on actual enterprise software, with the replication on, with the redundancy on, less than 10% of performance degradation was observed. And downtimes lasted for less than 1 second. I leave that to you. So we discussed this particular paper quite in depth. Please go through the paper that I have on the screen here. Kudos to the researchers who did this, and it's a beautiful paper. Please go through it. I will attach the link in the description below. That's all from my side. I just wanted to share this fascinating paper. Yeah, I think that's all from my side, and thank you for joining, and I'll see you next time.